Hello friends, so in this lecture we are going to discuss about the implementation of half adder using universal logic gates. So in the digital logic design, you must be knowing that the NAND gate and the NOR gate are the universal logic gates, and using only the NAND gate you can implement any digital circuits. Similarly, the case is for the NOR gate. You can implement any digital circuit using only NOR gates. Okay, so that we are going to discuss in this class. So before we jump implementing the half adder using the universal logic gates, we will briefly revisit the concept of the half adder. So first of all, the block diagram. The half adder block is considered as having two inputs as well as two outputs. Both the inputs are the binary bits. Okay, so A is a binary bit as well as the B is another binary bit, and when we both binary bits added, okay, when we add them, we finally get the sum as well as carry. So it might be possible that when we add two binary bits, the sum will be having a value, but there will be no carry, and sometimes we will be having a carry. Okay, so that is the case. So again, the 7 plus 5, the if the both are the decimal numbers, for the simplicity, I have taken a decimal number. Okay, so 7 plus 5 is 12. So among in that 12, we have 2 is a sum and 1 is a carry. So that was the understanding about the block diagram. Now we will go for understanding about the truth table. So since we have two inputs, so we have four sequences, that is 0 0, 0 1, 1 0 and 1 1. And similarly we have two outputs, that is sum and carry. So for the input 0 0, the sum is 0 and the carry is 0. For the input 0 1, we have the sum is 1 and the carry is 0. Similarly, for the input 1 and 0, we have sum 1 and the carry is 0. And finally, for the input 1, 1, okay, so when we add 1 and 1 in a binary, the output is actually a 1, 0. So in the 1, 0, the 0 is a sum and the 1 is considered as a carry. So that's why the output for the sum is 0 and the carry is 1. So this is about the truth table. And finally, let us revisit the circuit design of the half adder. So again, the inputs remain same, that is the two inputs A and B. So in order to implement the sum, we take the XOR gate. Okay, so when we supply the input A and B to the XOR, finally it will generate the sum, and when we supply the input A and B to the AND gate, it will implement or it will give us the carry. So this is the logic design, circuit design for the half adder. Now here in this case we have taken XOR gate as well as the AND gate. But suppose there is a question that you are no longer allowed to use the XOR AND gate or any other gate except only the NAND gate. So in that case, you have to transform the circuit in such a way that you will only use the NAND gate, but at the same time you will implement the behavior of the sum as well as carry. Okay, so first of all, let us start with half adder circuit design using only the NAND gate. So this is a typical circuit design for the half adder, where we have taken five different NAND gates. Okay, and then we will see whether this particular circuit will work or not for the implementation of the half adder. So similarly, you have to make sure that there will be only two inputs and two outputs, and that will be the behavior of the half adder. So first of all, the A and B input are connected with the NAND gate. Okay, and then after we take two separate NAND gate. The one NAND gate is having one of the inputs as A and another input is the output of the first NAND gate. Similarly, we have the another NAND gate where one of the input is the B and the second input is the output of the first NAND gate. And finally, we will take one more NAND gate to implement to finally get the output as a sum. Okay, so this final NAND gate is having an input from the previous output of the NAND gate. And to implement the behavior of the carry, what we can take, the output of the first NAND gate itself is connected with the both the inputs, and that NAND gate will ultimately give us the behavior of the carry. So if you want to understand that behavior in a step-by-step manner, so let us take an example. So the output of the first NAND gate, so the NAND is nothing but the AND followed by the NOT gate. Okay, so A and B, if we supply the AND gate, so AND gate will output as AB followed by the NOT gate, so that is AB complement. So now let us go back to the topmost NAND gate where one of the input is the A and another input is the AB complement. So the inputs are A and AB complement. So finally the output of this NAND gate is AB complement, and then after the whole complement. That means the NAND gate is a AND followed by the NOT gate. Similarly, for this particular NAND gate, the input is B and AB complement, so the output will be B and AB complement whole complement. Now we have final NAND gate where the inputs are from the output of the previous NAND gate. So that means one of the inputs is AB complement whole complement, and the another input is B and AB complement whole complement. And now when we will apply the NAND gate over that, we will finally get the output as a complement B plus AB complement. So you have to work a bit of here, okay, so that you can simplify the expression, and finally after the simplification you will be able to obtain that A complement B plus AB complement. Now come back to the final NAND gate that is used for the implementation of the carry, where both the inputs are AB complement. Now we have both the inputs as AB complement, and when you will simplify this further, you will ultimately get the AB as a final output. So this is the entire circuit design for the implementation of the half adder using only the NAND gate. The things that you need to remember over here is that we have taken 5 different NAND gates for the implementation of sum and carry. Now let us move towards the implementation of the half adder circuit using only the NOR gate. So there is a correction over here on the title. Okay, it has been written as a NAND, but we are going to implement this is using the NOR gate. So again, here also we have taken the 5 different uh, NOR gate. Okay, so the inputs are remain same A and B. So let us understand this circuit bit by bit. So the output of the first NOR gate will be A complement and B complement. So the inputs are A and B. So this XOR, sorry, NOR gate is nothing but a OR followed by the NOT gate. So first of all, the inputs are A and B. So A plus B is considered as the OR gate followed by the NOT gate. So A plus B whole complement. So A plus B whole complement will be considered as A complement and B complement. Now the input A is connected on the with the topmost NOR gate where both the inputs are considered as the same input A. So the output will be A complement. Similarly, we have another NOR gate where both the inputs are B, so the output will be B complement. Now we have the NOR gate over here where one of the inputs is A complement and another input is B complement, so the output will be AB. So you need to work for here, a bit of work required from your side, that how this A complement B complement when applied as an input to the NOR gate will generate the output as AB. Okay, so this is nothing but a simplification process, so that you have to work on your own, but the ultimate output will be AB. So now that AB, whatever the output is connected with the carry. So that carry, as we know that the carry is nothing but the representation of the AND gate. So that is A and B. Now that AND gate output, sorry, the NOR gate output is considered as one of the input to the final NOR gate, and then another input is the output of the first NOR gate. So AB is one of the input and A complement and B complement is another input. When you will apply it to the NOR gate, finally you will generate the A complement B plus A B complement. So this is the way you can implement the half adder circuit using the NOR gate. So that was the purpose of this lecture. We will see the full adder circuit design in the next lecture. Thank you for today. Thanks.